CQ, CQ, CQ 20 meters.
Radio Society. Tonight we're going to look at an introduction to apparent and true power. Now, before we get into the real meaty stuff, I'm going to get charged up here and let's look at a little bit of refresher on the basic foundation of our electrical and electronic world. Remember Ohm's law? Voltage is equal to current times resistance. This is the very basic fundamental equation that all of electrical and electronic systems are based upon. People often have a different understanding of what energy and power are. Energy is defined as the ability to do work and heat is a form of energy. Work is the amount of energy transferred by a force acting through a distance. So without a distance component, we have no work being done. Now, Ohm's power law is of course derived from the previous equation, and power is equal to current times voltage. Now, this is fine when we're talking about direct current or an instantaneous value on an alternating current cycle. Ohm's power law makes no reference to frequency. There's no time value in Ohm's power law because it is referring to direct current that never changes or an instantaneous value of a sine wave. So there's no time element. Ohm's law, in the form we're most familiar with, doesn't work in alternating current circuits, except for that instantaneous value. Now here is another meme that shows the formulas that may be used to find power, voltage, current, or resistance by knowing any two of the other elements that you may know. So frequency becomes a factor when we start talking about alternating current. When waves begin, when we talk about waves, as in radio waves, we have a critical factor not previously addressed. Ohm's law doesn't deal with frequency. It doesn't exist in DC circuits. An AC sine wave is constantly changing in amplitude and direction. So conventional Ohm's law won't work for us. What we need to know is what effect the alternating current is having on our equipment, the components through which this current flows. In an alternating current circuit, the simple P equals IE works fine in to give us an instantaneous value. And that result that we get using P equals IE is apparent power. That's the power that appears to be available to do work. True power is effective power. This is power that equipment can actually use, in our case, to drive a signal. So this is what gets it out into the air and out to people who are listening to our transmissions. But first, before we can calculate the effective power, we have to know, excuse me, we need to know how much power is required to drive that signal and calculate the effect that AC power has that's equivalent to DC power. For example, how much AC power does it take to produce the same amount of heat in our radio components as compared to DC? To find that effective power, we need to use a different form of calculation known as root mean square, or RMS. Most of you have seen RMS in the literature in various places. RMS is a calculation that provides us with the effective value. Now, taking an average doesn't do the job. We have to use this RMS calculation, and you don't need to drag out your calculator to figure it out. As it happens, RMS resolves to a constant value, and we only need to know what that value is. RMS is always 0.707. The effective AC values, or RMS, is less than the peak shown on an oscilloscope. If this image were of an oscilloscope screen and we were looking at plus or minus 1 volt, then that dashed line would represent the 0.0707, or the RMS value. Now, when we look at our household wall receptacle, and we stick a voltmeter in there and we see 120 volts. What we're seeing is the RMS value being read by the voltmeter. So what we really have is a peak-to-peak value of 170 volts. The RMS times 170 gives us the 120 volts that we're reading on our voltmeter. This is the effective voltage that we're reading with our meter. And unless the value in your whatever literature you're looking at, unless the value is specified as peak to peak, you can assume that it's an RMS value, because that's what we really want to know, is the effective value of voltage, current, power, and so forth. So if we look at this AC sine wave, we have voltage as the blue line, the red dashed line is current, and the green wave, no, it's not two-lane, this is our green power wave here. And notice that power is always positive because our current and voltage start from zero at the same time. They reach their peak and cross through zero again at the same time. Voltage and current are both moving in the same direction and pass through zero at the same time. This is said to be in phase. Voltage and current are in phase, and the power produced by this AC in phase system is always positive, because when you multiply a positive value by another positive value, the result is always a positive value. So we have positive power wave there. Now, in purely resistive systems, the current and voltage are in phase. And so voltage and current pass through zero at the same time and go in the same direction. Once again, note that power is positive and stays positive. Some examples of resistive loads might be incandescent lights, resistance heaters. If you have an electric hot water heater, electric stoves, and of course, resistors. Okay, so why would they not be in phase? Why would voltage and current not be in phase with each other or synchronized? What could cause a circuit to not be purely resistive? Reactance is the answer to that. In alternating current circuits, we have to deal with inductors and capacitors in various forms, and these components produce a reactance, which cause voltage and current to become out of phase with each other. Now, this is a little peek ahead at the relationship, the phase relationship between a capacitive system and an inductive system. And if you notice at the top, in the top graph, we have current leading our voltage by 90 degrees. Likewise, in the inductive system, we have voltage leading current by 90 degrees. So let's look at induction and inductance. Here we have an example of a simple electric generator. Now, this generator consists of a winding, in this case a single loop of wire, suspended between the two poles of a permanent magnet. So right now it's sitting in the maximum flux of the magnetic field. That coil of wire, each end is connected to slip rings. Now the slip rings then in turn are connected to either side of our load, in this case an incandescent lamp. So what's going to happen here is, as we rotate that coil of wire in that magnetic field and rotate it, what's going to happen is the coil of wire is going to pass from the highest magnetic flux into a much weaker magnetic flux. So when that coil has rotated 90 degrees from where it is right now, we will be at the minimum magnetic flux, and our voltage will be zero. But as we continue to rotate, that coil of wire will start to enter a higher flux region, and we'll induce a current flow in that loop of wire. So that's how a generator works. We're rotating a loop of wire inside a magnetic field, and that changing magnetic field induces a voltage and current flow in the wire, through the load, and back to the wire. Inductance is a property of coils and other devices that contain coils or windings. When we'll look at the formula for inductive reactance on the next slide, and we'll see L is the symbol we use for inductance. And the unit of measure for inductance is henries. So, inductive reactance. Inductive reactance is a reaction to the change in voltage. Current is going to lag 90 degrees behind the voltage. As the voltage change ends, when we've rotated 90 degrees, the voltage goes from 0 to a peak value. And once it reaches that peak and starts to come back down again, the voltage decreases and allows current to flow. So this inductive reactance induces a counter EMF, or a counter voltage, that holds the current back until it reaches its peak and starts to come back down again. Once the voltage reaches a peak and starts to come down, then we'll see current begin to flow. And when voltage reaches 0 at 180 degrees, we'll see that current reaches its maximum, or its peak. Now, we use X to represent reactance. In this case, we're using the subscript L for inductance. So this is inductive reactance. And the formula is 2 pi times the frequency times the inductance in henries. And inductive reactance is directly proportional to any change in circuit frequency or inductance. So here we have a direct change. If frequency goes up, inductive reactance will go up. If the inductance goes down, inductive reactance will go down. So this is a direct relationship. Inductance creates an opposition to any change in circuit current. I can't emphasize enough that all of this reactance is a result of a change. That's why DC circuits don't see reactance at all. So inductive reactance effects, we're looking at power. And power is the product of current and voltage. We know that from basic Ohm's law. What happens if either one of these is zero, then power is zero. So as we look at the graph down at the bottom, we can see that power is zero anytime either current or voltage passes through zero. Unlike a resistive system, a purely resistive system, we see here that there is a phase shift. In this case, we have current leading voltage. So this graph is of capacitive reactance, not inductive reactance. But when one value, either current or voltage, is negative and the other is positive, the result is going to be negative. Because when we multiply a negative times a positive, we always wind up with a negative. So what we see here, if we look at this green wave again, we'll see that power is not always positive. For 1/4 of the cycle, it is positive. For the next quarter cycle, it's negative. Another quarter cycle, it's positive. The last quarter cycle, it's negative again. So for effectively half of the cycle, power is negative. What? What? Negative power? Who ever heard of negative power? Well, we're going to talk about it now. Positive and negative reactive power cycles are equal in magnitude and duration. And so what we're going to see with reactive power is similar to active power. The difference is that we have this phase shift which causes us to have negative power as well as positive power. And because we have this positive and negative power, what we're seeing is power goes out on one half cycle and comes back in on the other half cycle. The reactance of an inductor produces no power. So reactive power doesn't produce any power at all because it goes out on one half cycle and comes back in on the next half cycle. The net energy produced by reactive power is zero. Hence, no work is being done. Reactive power produces no work. It just goes out, comes back in. We measure reactive power in VARS. volt amps reactive. That's why we call it wattless power. We can't use units of watts because we don't use it, it's not power. It does no work, so we can't use the units of watts. So, the thing is that even though it does no work, current does flow as a result of reactance. So we have current going out on one half cycle and coming back in on the other half. Actually, it's quarter cycles as we saw before. But the net effect is one half cycle, we've got power going out. The next half cycle, we've got power coming in. So we do have electron flow through the system by virtue of reactance, reactive power. This is real electron flow. And because it is real electron flow, reactive power creates heat. That electron flow back and forth, even though it's coming in and going out and doesn't do any work, we still have electron flow and we get heat. The heat that's produced through reactive power is just as real as the heat that is produced from active power. So, we have to deal with this heat. We have different mechanisms that we use to get rid of this heat. But because this heat does no work, is why VARS are often referred to as wattless power, because we can't use the unit of watts to describe this power. Heat's produced, but there's no work being accomplished. The heat produced by reactive power has to be dealt with in the system. We have to be able to get rid of the heat that's produced so that we don't burn up the equipment. So different mechanisms are designed into our equipment to deal with the heat that's produced from the system. We've got heat sinks, we've got fans, we've got different methods of passive and active cooling that are designed into the radio equipment to get rid of this heat. So because we have this reactive power to deal with, the cooling capacity has to be greater than which would be required to deal with the heat from your output power. So you may have 10 watts of output power, but along with that, there is some reactive power component that also produces heat. So the designer of the equipment must consider VARS in addition to watts to provide sufficient cooling to prevent damage to the equipment. So that's why we are concerned about VARS, is because it can limit the amount of active power that we can produce. If we haven't got something to compensate for the VARS and provide the cooling for it, then our active power output has to be reduced to be able to carry the heat from both active and reactive power. Going back to the mag lab again, we'll go here and see another animation here that will illustrate the effects of inductive reactance. Now, for those of you who've never been out there before, the National Magnetic Laboratory at nationalmaglab.org has a lot of really cool electrical and magnetic animations and tutorials that really help to understand and describe many of the things that we deal with in electronics. So here we have a battery, a knife switch, a series of incandescent lights, and an inductor. Inside the inductor, we have a highly permeable core, an iron core, and by changing the position of that core, we vary the inductance or henries of that inductor. So we'll start out with the battery and we'll turn it on. And we see our lights light up. So we've got a bunch of bright lights here being powered by that battery. Now, if we change the inductance of that coil, you see absolutely nothing happens. If you're thinking about the inductive reactance formula, what we're doing is we're varying the L value, or the henries, of that inductor. But frequency is zero because we're coming from a battery. Since frequency is zero, inductive reactance is zero. So we'll turn it off and swap our power source over to alternating current, and we'll turn it on again. Now we will adjust the inductance. Now we have some constant frequency, so frequency exists, and we'll vary the inductance. And as our henries increase, the L value increases, inductive reactance increases, and our current flow goes down. We decrease the inductance, we increase current flow. Inductive reactance goes down, current flow goes up. We'll do that one more time. So this illustrates the effects of inductive reactance. Thank you, National Mag Lab. Again, I encourage you to just go take a look at the nationalmaglab.org education section, and they've got a whole bunch of really neat stuff in there. So we've talked about inductance and inductors and inductive reactance. We haven't hit on capacitance yet. Well, we got a lot of capacitors in our radios too. So we'll talk about how capacitance affects our sine wave, and we'll look at how capacitance creates an opposition to any change in circuit voltage. Now notice capacitive reactance opposes a change in voltage. Inductive reactance opposes any change in circuit current. Capacitive reactance opposes voltage. Inductive reactance opposes changes in current. So many of us may have under your kitchen sink a set of water filters that feeds a little spout on top that you can get really good clean drinking water from. Well, you have your regular water supply coming to the inlet to the filters, and on the outlet of the filters there's a tank. This tank has a pressurized diaphragm in it that is preloaded with some nitrogen pressure, and because these filters create such a resistance to water flow, if you didn't have this accumulator and you tried to get water, it would run very, very slowly because of the resistance through the filters. So the people who provide those filters put in this accumulator, and when you're not using water, the water slowly comes through the filters and into the accumulator until the water pressure inside the accumulator is balanced with the water supply to the filters. So when you use the water, you're going to have a pressure drop, and that accumulator, because of the charge that's on it, the pressure charge on it, is going to continue and hold that water pressure for a few seconds so that you actually get a usable stream of water. And that's an accumulator. And notice the accumulator doesn't produce any water. It just accepts a charge of water and discharges that water when the pressure in the system goes down. Well, capacitors basically do the same thing. Capacitors can temporarily store electrical pressure or voltage. Capacitors consist of a pair or multiple pairs of electrically conductive plates that are separated by a dielectric, some non-conductive material, might even be air. It is important to note that capacitors cannot produce voltage like a generator or a battery. You may have a well pump or a tank under your kitchen sink that holds water, as we just talked about, and that accumulator accepts a charge of water until it's needed. And when it sees the system pressure go down, it discharges water from that accumulator for use to try and hold that water pressure up for as long as it can. So, how do capacitors actually work? This can be pretty confusing to people. So we're going to go back to the National Mag Lab and look at a capacitor. And I'm going to reset this rascal. Okay, here we have a battery that feeds into a double throw single pole switch that can be aligned to the capacitor or to this little motor up here, and the motor has a little pulley on it that's connected to a string to a weight down at the bottom. So first of all, what we're going to do is we're connecting the battery, and we see current flow from the battery into the right-hand plate of the capacitor. Now, it appears as though we have current flow, but it's not really current flow through the capacitor because we have this dielectric in there that keeps the plates from passing electrons. So what happens is we actually have electrons from the other side are drawn off back to the battery. So now we have a deficit of electrons on the left side of our capacitor, and we have excess electrons on the right side of the capacitor. Now, if we flip our switch and connect the capacitor to the motor, we see electron flow through the motor, and the motor runs and draws that weight, and the electrons flow not back to the battery, but to the other side of the capacitor until we have zero potential difference across the capacitor. No voltage across the capacitor. We have a discharged capacitor. Going back to the battery, we'll charge the capacitor and build up an excess of electrons on the right side, and we'll draw off electrons from the other side, so we have a deficit on the left and we have an excess on the right. We go back to and connect our motor to the capacitor, and electrons flow from the capacitor through the motor and back to the other side of the capacitor. Notice there's no current flow to the battery. So that's how a capacitor works. And you can see that that capacitor only stores electricity. It does not produce electricity. So we'll go back now to our presentation, and we'll talk about capacitive reactance. So how does reactance come into play with our capacitor? Well, first of all, charging of a capacitor happens in both directions, positive and negative. So it charges in both directions. As current declines and the capacitor becomes charged, the voltage across the capacitor increases until we have a high voltage across the capacitor with no current flow. When the capacitor voltage hits its peak value, the capacitor is said to be charged. current begins to flow in the opposite direction as the capacitor voltage drives the electrons to the opposite plate and discharges. The current sine wave goes through zero in the opposite direction. So by absorbing these electrons or discharging the electrons, the voltage change is delayed. The result is that current will flow before the voltage goes up. And the current sine wave will lead the voltage sine wave by 90 degrees. The capacitive reactance is precisely opposite from inductive reactance, X sub L. This can be seen in the equation for X sub C, or capacitive reactance, as 1 over 2 pi Fc. The 2 pi F is common to both inductive and capacitive reactance. So we have a frequency component for both. But instead of henries, we have farads as capacitance. And X sub C is a reciprocal. It's 1 over 2 pi Fc. So its effect is opposite to inductive reactance. So some examples of capacitors that you might not even think of. Long transmission lines, power lines, are current carrying conductors separated by a dielectric. So a long transmission line produces an enormous amount of capacitance. Electroplating facilities. Here again we have positive and negative plates, and we have the electrons are drawn to one plate, and that is how the plating is done for electroplating, like chrome and other examples of electroplating. Synchronous motors and radio circuits all have some capacitive component. Now, capacitive reactance does the same thing as we said earlier. It opposes change in circuit current. Inductive reactance opposes any change in circuit current. Capacitive reactance opposes any change in circuit voltage. So reactance does precisely the same thing, but it works in the opposite direction. We have an opposition to voltage, but in an opposite direction. Capacitive reactance produces negative VARS. Given equal values of capacitive and inductive reactance, the net effect on the system is going to be zero. They'll cancel each other out. Total reactance is going to be the algebraic sum of inductive and capacitive reactance, since inductive reactance is positive and capacitive reactance is negative, what we'll do is we'll subtract the smaller value from the larger value to wind up with a net reactance, either positive or negative. But once again, no power is consumed by reactance. This is what I just said. We've got, you subtract the smaller value from the larger value, and the net is what you have left over, either capacitive or inductive. And this is a simple example. We have 1,500 ohms, and again, reactance, whether it's inductive or capacitive, reactance has units of ohms, just like resistance. So if we have 1,500 ohms of inductive reactance and 1,000 ohms of capacitive reactance, we're left with 500 ohms of inductive reactance. ELI'S coming. Some of you old folks like me remember that song. But here we'll look at E as the symbol for voltage. Everybody's familiar with that. I represents current. L is inductance in henries. And C is capacitance in farads. So let me introduce you to Eli, the Iceman. Eli is an easy way to remember that voltage leads current in an inductive system. Because we have the L in the middle, reminds us that this is an inductive system, and voltage comes before current. Ice, the Iceman, current comes before voltage in a capacitive system. So C tells us this is capacitive, and current leads voltage. So this all leads into impedance. Now we have resistance in ohms that everybody's familiar with, but we also have inductive and capacitive reactance, which are also in ohms. Impedance draws all three of these factors together. Impedance is the total opposition to current flow in an alternating current circuit. Total opposition to flow. And that includes the reactive components. So resistance, it's good to remember, resistance is a physical property of the material through which current flows. So we can change the type of material in a resistor, and that will change its resistance. We all know that gold is a much better conductor of electricity than carbon. So resistance is a physical property of the material. Also, resistance is not affected by frequency. And I hope you've gotten the idea now that reactance most definitely is affected by frequency. When we look at impedance, we include resistance as well as inductive and capacitive reactance to get a total opposition to flow in the system. And to do that, we have to use a vector. And this is an example of impedance as a vector. We have X sub L. In this case, we can assume there is no capacitive reactance because all we're seeing here is inductive reactance. If there was some capacitive reactance, we have enough inductive reactance to cancel it out. So we have reactance on the vertical axis and we have resistance on the horizontal axis. If we have some value of resistance and go up from that point to where it intersects with the reactance value, right there is the intersection of the two values, and we have the hypotenuse of a right triangle Z, which is our impedance. And angle theta here, we're not going to talk about that except to say that it's there, and we would use angle theta to calculate power factor, which is beyond the scope of this discussion. So, a purely resistive circuit has no reactance. Or when capacitive and inductive reactance are equal, the net effect is zero. And if we have a purely resistive circuit, there's no phase difference between voltage and current because the inductance and capacitance have canceled each other out. A purely resistive system is the most efficient system we can have. Now, I'm borrowing from my background in electrical power generation here. I've spent 40 plus years in electrical power generation in nuclear and fossil power plants. And this graph I'm using to illustrate a point, though we're going to ignore a lot of it. But this is a good example that shows this is a generator capability curve. And what it shows is the heat removal capability for a generator with a given hydrogen pressure. This particular curve here is based on a hydrogen-cooled generator. But if you'll notice over here, on the left side, on the y-axis, we have megavars, okay, or kilovars. But this is our reactive line. We have zero here at the middle where we have no reactive at all. And over here, this horizontal or x-axis is in megawatts, or in this case, thousands of kilowatts, which is megawatts. So here, if we think of this as being resistance instead of power, first of all, we go up from the resistance line and come over from our VARS line, and the yellow line represents the actual impedance of our system. Now, for this generator, we're carrying 40 pounds of hydrogen, and as long as we stay inside this D curve here, we don't have to worry about overheating the equipment. But watch what happens if we had 0 VARS. What we would have here, this 0 VARS, the blue line would go away. We'd have 0 VARS, and we go out to this same D curve, and this blue line shows how much additional power we could carry without overheating the machine. So this illustrates what I've been saying here about heat being the factor we're concerned about with regard to VARS. It's the heat produced by wattless power. The issue is heat. So now you can go forth secure in your knowledge and understanding of one of the least understood facets of radio station operations. You now know the magic and are a wizard of VARS. So I hope you've enjoyed this presentation. We don't have a facility for doing questions and answers, but again, I'm Skip Hagan, Kilo Oscar 4, Delta Golf Kilo, and I hope this presentation has been of benefit, and you can get in touch with me through the website, and if you have any other questions or would like some more information, I'll be glad to help you out any way I can. And my contact information is on the YCARS website for members. And with that, I will bid you adieu and thank you for taking the time to watch this video.
Parks on the air calling CQ 20 meters.